Greetings everybody and welcome back to another video. Uni started today, so like the maths building is always full, so that's why I'm in the physics building on this old blackboard here today. Don't even know if I can go back into the maths building unless I stay like until the evening or the night time or something like that. I don't know, we'll see. But yeah, what are we doing today? We're taking a look at this improper integral. It's been a while since we did a bit of contour integration here on this channel, and today we have quite an exotic one. I found this one on MathStackExchange, and I suggested it to Maths505. If you guys follow him, you would have seen the video on this integral that he evaluated using the real methods. It took him like a few minutes to do. But yeah, we're taking a look at the complex version of this guy today. It's probably going to be a very long video. I have like 2 pages of notes written out on this thing. But yeah, we will see how things go. We are not here for efficiency today. We're here for the experience of having such an exotic contour. If you guys seen the thumbnail, then this guy's gonna have infinitely many branch cuts. Like, when do you ever see infinitely many branch cuts? Like, this guy's absolutely ridiculous. All right, so how on earth can we get started with this thing? At first, I want to investigate this log function because we have a log of 1 plus e to the x. That's a bit annoying to work with, at least in the complex plane. So let's investigate that function a little bit there. Now, notice we have a logarithm. So in particular, there's going to be a few branch cuts. So let's investigate. Log of 1 plus e to, and I'm going to replace x with z over here. Let's take a look at this guy. Now, we know the logarithm has branch points at exactly z equals 0. So what we can do is we can solve the inside over here for 0. So we're going to let 1 plus e to the z be equal to 0, and we can rearrange this guy a little bit. So we have e to the z equals -1, which we can rewrite as e to the I times pi. But we can also have e to the 3i pi or 5i pi. So in general, you can just multiply this exponent here by some kind of 2k plus 1, where k is an integer. And now if you just compare the exponents over here, we get z is equal to I times pi, and then 2k plus 1. So we have branch points along the imaginary axis, going up every odd integer multiple of pi. Okay, so branch points, those are fairly simple to figure out. So branch points over here. Now we need to take a look at the branch cuts, and the branch cuts are going to be slightly more tricky to work with. And so how on earth can we get the branch cuts of this thing? Well, we have the logarithm over here. Now remember the logarithm, we can rewrite this. So log of 1 plus e to the z, we can rewrite this. Well, the real part is going to be the logarithm, absolute value, of 1 plus e to the z, and then you have the imaginary part, which is I, times the argument of whatever is on the inside, which is 1 plus e to the z. Now, usually we just have some kinds of z minus 1 or z minus I, or some linear thing inside of this argument, so it's pretty easy to figure out what the branch cuts will look like. But here we have 1 plus e to the z on the inside. That's going to be a bit tricky to do. So let's choose a particular branch for the logarithm. There's infinitely many branches you could pick, but what we can do is we can just choose one. So we're going to choose in particular the argument of 1 plus e to the z to be on the interval 0 to 2 pi. Let's go for this one. You could take negative pi to pi, doesn't really matter. Things are just going to be slightly reversed, but let's take 0 to 2 pi for this video. Okay, so now we want to take a look at what the branch cuts in the z-plane would look like. So we can draw out a few pictures over here to kind of see things slightly better. I'm going to draw up, let's do 2 complex planes over here, and I'm going to do 2 more complex planes down here, and you'll see why in just a second. So this one over here, this is the z-plane over here, and then we have, let's say, the w-plane where w is equal to 1 plus e to the z. Now we know the argument of this guy is going to be 0 to 2 pi. So in particular, in the output plane, we're going to get a branch cut over here. And we want to see what the pre-image of this branch cut is in the z-plane, pretty much. All right, so how can we see what the branch cuts would be in the z-plane? Well, essentially, notice that this branch cut over here, this is a positive real part, and we're just changing between positive and negative imaginary parts. So if we can see what the real part of our function on the z-plane looks like, and the imaginary parts as well, we can roughly figure out what the branch cuts should look like. So what would that look like in particular? What I'm going to do first of all is rewrite 1 plus e to the z in the following form. So 1 plus e to the z is equal to 1 plus we have e to the x and then plus iy, but this is just e to the I times y like so. And now I can expand this e to the I times y using Euler's formula. So this is 1 plus, we have e to the x, then we have the cosine of y, and then we also have, so this guy's the real part, and then we have plus the imaginary part, which is I, and then sine of, or no, e to the x first, and then we have the sine of y. So we have the real and imaginary part of the function, 1 plus e to the z, right over here. So let's take a look at the imaginary parts first, because that's going to be slightly simpler to work with. Notice that e to the x, first of all, that's always going to be positive, so yeah, don't have to worry about that too much. But how about this sine of y over here? Sine of y, it can change its sign. So in particular, if our imaginary part of y over here is, let's say, on the interval 0 to pi, then our imaginary part is going to be positive. So let's take a look at the plot of the imaginary part of 1 plus e to the z here. So when we're between, let's say, yeah, an imaginary part of 0 and imaginary part of pi, we are going to have some kinds of positive imaginary parts. Let's do that in red over here. So there's a positive imaginary part when we go up to pi, and then when we go from, let's say, pi to 2 pi and so on, we're going to have a negative imaginary part. So you get the idea, you have these kinds of strips running over here. So we get these strips every single pi pretty much for the imaginary parts. So that's yeah, pretty simple there. Now how about the real part of the function we're working with? So real part of 1 plus e to the z. This one's going to be a little bit tricky to work with. I ended up just graphing it on Desmos, but what we can do is you can take a look at the real part, 1 plus e to the x cosine of y. Now this is just a relation between x and y. You can take a look at where this is 0, so if you plot it on Desmos or something, what you get is a bit of a funny looking region. So we have pi over here and it's negative pi, let's say. What you get is kind of like these quadratic looking curves. They're not quadratics though, because, well, we're working with exponentials and trig functions here. But essentially what you get is this whole region here is going to be positive for the real part. So if you plug a number in z anywhere in this red shaded region, you're going to get a positive real part for your function. But if you're in these areas over here, or these regions, you're going to get a negative real part for your function. Negative and then yeah, everywhere over here is positive. And of course this continues every odd integer multiple of I times pi. So we have I times pi here, then we have negative I pi, and then you'll have another little region at negative 3 times I times pi, and 3 pi I, and so on. You get the idea, hopefully. Right, so we know that the branch cuts on the output space. This is precisely where we're on a positive real part, and we're changing between positive and negative imaginary parts. So remember, we want a positive real part, so we're on this red region somewhere, but we want to change between positive and, yeah, negative imaginary parts. And there's only a few places that this could be, actually, because we can only have a branch point at negative pi, pi, and so on, so 3 pi, and you get the idea. So at these points over here, which means we can't really go to the right, we have to go back to the left. Along these lines here, where we change from a positive to a negative imaginary part. Right, so we need to be on this red region for the real part, and we need to run out of these branch points over here, and we need to select the paths where we're, changing between positive and negative imaginary parts. So that gives us these branch cuts to work with over here, which go directly to the left, and they come out of these branch points that we have already. So this is precisely going to be the plot of the branch cuts that we're going to have for the function. And yeah, I don't know if you can make the branch cuts run directly up or directly down, and you can control each of the branch cuts at each of these branch points over here. I don't know how to do that. Maybe it's possible, maybe it's not. All right, so now we're ready to define our complex function. So we're going to let f of z be equal to, we have our integrands over here, so z log of 1 plus e to the z divided by 1 plus a z squared and then squared. And we know exactly where the branch points are, so I'll just write it down over here. And notice we're going to get some poles as well. So poles, these are going to be double poles actually, because we have this squared here. So we have z is equal to plus or minus I, and these are double poles, or poles of order 2. Okay, so we have this so far. Now, how should our contour look? You already saw in the thumbnail. It's going to be pretty exotic because we have infinitely many branch cuts going on over here. So yeah, we want to somehow construct a nice enough contour that we can use. So here's the proposal here. Let's do a plot of the complex plane here. So we know we have some poles at plus or minus I here, so that's pretty simple. Okay, and we also have some branch cuts at pi, 3 pi, 5 pi. So this is not to scale, I think, but yeah, roughly. And then we have our branch cuts running out over here. So how can we construct a nice enough contour for this? Well, we want to run from negative infinity to positive infinity. So let's start at some negative r over here and run up to some positive r. So we really want to go along this path here. Now we want to turn this into a contour. We need to complete the contour. So, I mean, the only nice option is to, well, we can try go up over here. And we kind of want to enclose this pole so we can use the residue theorem and so on. Now, the problem is we have infinitely many branch cuts on the left-hand side, which we need to, yeah, traverse somehow. So how about we go all the way up to infinity, so wherever, and then we start coming down over here, but we're going to run into this, well, one of the branch cuts. So what we can do is we can go all the way back to the imaginary axis, do a little loop around, and then go back out. And then we can continue on our arc, and then go back in, do a little loop, come back out, go back down along the arc, in, loop, and out, and then we complete the contour that way. So there's going to be infinitely many paths, you could say, because we have infinitely many branch cuts we need to do a detour around. But yeah, this is the contour that you could use. And yeah, as I said before, the branch cuts, I don't know if you can make the branch cuts go all the way up, in which case you can just have a contour which looks something like this over here. So you have all the branch cuts going up this way, and on the negative side you have all the branch cuts going down this way. This would be a much nicer contour to use, but I don't know if that's possible. So we're just going to use this contour that we have here, and this was actually the contour that's one of the people who answered the question on Stack Exchange used as well. So we have the contour, let's call it a C. Now let's name a few of our paths over here. And by the way, the poles, negative pi, positive pi. So in terms of the path, let's call this path over here. Well, first of all, these are branch points at pi. We have 3 pi I and then 5 pi I. So let's call those little circle paths, let's call them gamma, let's say 5 pi or something. And then we have gamma 3 pi, and then we have gamma pi over here. And by the way, our contour is going in the positive direction, so we're going anti-clockwise like so. So something like that. And we'll call the arc that goes all the way around, let's just call it a gamma, why not? And then how about the paths that go along these branch cuts over here? Well, let's call the first one, let's do psi, and then we'll put a positive sign here because it's above, and we'll do subscript pi, like so. And then we'll do the one underneath, the psi subscript pi, but negative because we're underneath. And then you get the idea. So this guy up over here, this would be psi negative 3 pi, and then psi positive, positive 3 pi, and then you kind of have psi negative 5 pi, and then psi positive 5 pi, like so. So those are our branch cuts done. So let's write out our integral now, somehow. So we have the contour integral over C of our function f of z, dz. What exactly is this going to be? Well, we need to sum all the paths that go around the branch cuts. So let's do that in one big sum over here. So we have the sum running from k equals, let's do 0 up to infinity, of, that's going to be integral over psi positive 2k plus 1 times pi. So that's all the branch cuts that go above, and then how about the ones that go underneath? That's going to be integral psi negative 2k plus 1 times pi. And then we also have plus the integrals that go around the loops over there. That's going to be integral of gamma 2k plus 1 times pi. Right, so these three integrals, they go around each and every single one of those branch cuts over there. And then we start the integral, let's write it down over here because we've run out of space. The integral from negative r to positive r, at least in the limits anyways, of the function f of z dz. And we know this guy, what this guy is going to evaluate to already. That's going to be our original integral I, which I always forget to label at the very start of the video. So this guy over here, that's going to be our I. And then we also got the gamma integral that goes all the way around. So we have plus integral over gamma, like so. Okay, so for the purpose of keeping this video short as possible, what I'm going to do is I'm going to assume that the integral over gamma and the integral over these little gammas over here, they go to 0. I might do another video on the proof that it's not too tricky to do. But yeah, these are going to go to 0 because this one goes around to branch cuts or branch point, and this one, well, as you can clearly see, the denominator is just going to clearly outgrow the numerator. So we have the integral over these guys over here. We can assume that they vanish off to 0 in the limit as r approaches infinity. So basically all that's left for us to do in this video is to evaluate this contour integral and just evaluate infinitely many of these path integrals that go above and below the branch cuts. So let's take a look at this contour integral first. It shouldn't be too tricky to do, hopefully, because that's just going to be a bit of residue theorem. So let's take a look at the residue calculation on this blackboard and maybe the other integrals as well. So first of all, contour integral over c of the function f of z dz. What exactly is that going to be? That's going to be 2 pi I times the residue. And now we only pick up one residue because we are only going around to that one pole at z equals I. So the residue at z is equal to I of the function f of z. So now, because it's a double pole, we need to use the formula for residues at higher order pole. So it goes something like, let's see if I can remember it. It's 2 pi I, and then what you do is you take 1 over the order of the pole minus 1 factorial. So that's going to be 2 minus 1 factorial. And then you take something like the limit as z approaches the poles, as z approaches I over here, of the derivative, so d by dz, to the order of the pole minus 1, so because the order is 2. We just take the first derivative over here, and then what you take the derivative of, it's z minus the pole to the order of the pole, which is 2, times the function, which is going to be z. We have logarithm of 1 plus e to the z, divided by 1 plus z squared, but the whole thing squared. So we have this whole mess here to evaluate and simplify. So where can we get started? Well, this 1 plus z squared, hopefully you can see it's not too tricky to see. We can rewrite this as a z minus I squared and then z plus I squared. So this is nice because it's one of the factors that are going to cancel here. Like cancel, cancel. So we need to evaluate the derivative of, this mess over here. So z log of the stuff divided by z plus I squared. Let's see if we can do that. So we have equals, we have the 2 pi I, this factorial stuff is going to be 1, so it's just 2 pi I. We have the limit as z approaches I. Now we take the derivative over here. Okay, now we have to be a bit careful. So we have to quotient rule this, I believe, because we have this whole numerator part. Let's call the numerator u, and then we'll call the denominator, which is now this guy, we'll call that v. So quotient rule goes something like you do v and then u dash. So that's going to be, let's see, z plus I, that's our v squared, and then u dash. So we have to differentiate this guy. Now we have to use a bit of product rule. So how does product rule go? You differentiate the first guy, which is 1. You keep the second guy, so log of 1 plus e to the z. And then you add, you keep the first guy, but you differentiate the second guy. Derivative of log is something over the inside. And then you chain rule. Derivative of the inside is e to the z. So this is v and then u dash, this whole guy, which is the first part of the numerator of the quotient rule. Now you have to do minus. We have u and then v dash. So u stays the same. So z log 1 plus e to the z. And then we have to do the v dash over here. But what's v dash? It's just 2 times z plus I pretty much. So just chain rule if you want. So 2, and then we have a z minus, or z plus I rather down here. Okay, that's a very long numerator. So all of this gets divided though by v squared, which in this case is a z plus a 1, or z plus I. It's squared, but we square it again, so it becomes a 4th power. Okay, so now we have to take the limit. So nothing should blow up or anything. So we have 2 pi I. What happens if you take the limit? Well, z plus I, that's going to be I plus I. So 2i squared is negative 4. So this guy over here turns into a negative 4. How about this z plus I? Well, it's 2i raised to the 4th, which is exactly 16. So this guy over here turns into 16. What else can we simplify? Well, not much, I think. So let's just try to simplify this as much as we can. Also, we have this negative 4 here. So let's write negative 4, we'll expand here. So negative 4 log 1 plus e to the negative, or just positive I believe, And then we have a negative 4 once again. Z is going to be I, so we have I, and then e to the I over 1 plus e to the I, okay? And then we have a negative 2, but then we have a z, which is I, so negative 2i here. And then this is also going to give us a 2i, so negative 2i times positive 2i, positive 4. Then we have a logarithm of 1 plus e to the I, like so. So this is end of bracket, and then we can just divide by 16 at the front. Why not? Okay, so a few nice things are going to cancel. First of all, we have those logarithms there. Oop, I dropped some chalk. So we have the logarithm of 1 plus e to the I, negative 4 of that actually, and then we have this positive 4, so that cancels out. That's really quite nice. And then we are basically just left with this negative 4 times stuff over here. Let's see, 4 we can cancel with 16, so this is going to be a 4, and then this is gone. But 4 we can cancel with the 2 as well, so this is 1, but this turns into a 2. Okay, so overall, what on earth are we getting? We are getting, that's going to be, we have a negative here, so negative 1/2. We have I, okay, and I forgot this pi times I as well, so I should put pi, and because we have I and then an I here, that's going to be a negative, so it cancels with this negative out over here that we have, so negative I, positive I, and then we just have e to the I divided by 1 plus e to the I, and we can multiply the top and the bottom by e to the negative I, and that's going to give us 1 divided by, and we're going to have 1 plus e to the negative I believe. So that should be the value of the contour integral. Let me just check my notes to make sure I didn't mess up on anything. Yeah, so that should be it over there. So in my notes, I just wrote this as, yeah, let's just leave it like this. Why not? That's fine how it is. So that's the residue done. That was a pretty annoying computation because of the double pole. But now we are ready to move on to the slightly more interesting part of the video, which is calculating the integrals along those branch cuts over there. So how can we do this over here? I'm going to get rid of this residue calculation. So I know it's pi on 2 divided by that weird stuff. So this guy is going to be pi on 2 times 1 over 1 plus e to the negative I. That's the value of the contour integral there. So let me just erase this second blackboard, and then we'll continue with the branch cut stuff. All right, so what we want to do now is we want to calculate these integrals that go along the branch cuts. So let's take a look at the integral of psi positive. All right, so integral psi positive. And just to simplify the notation a little bit, I'm going to choose some lambda over here, which is going to be a placeholder for this 2k plus 1 times pi, which is the imaginary part of the part that we're going along. So we are basically at an imaginary part of lambda here. So we have integral of the function f of z dz. Now the positive side here, what's it doing? It's going from, well, it looks like it's negative infinity all the way back to 0 there. So if you take the limit, this is going to turn into the integral from negative infinity back to 0. Now we need to parameterize this guy a little bit because here we have z is equal to, that's going to be some parameter, let's say t plus I times lambda. So our dz is going to be equal to a dt here. Okay, so if we plug in the parameterization, what do we get? We get, first of all, we had the z there, but that's going to be t plus I lambda. And then we have the logarithm of 1 plus e to the z, which is going to be t plus I times lambda. And all of this is going to be divided by, well, that's going to be 1 plus t plus I times lambda. This thing is squared, and then this thing is squared, and then everything integrated with respect to, t. Now we can take a look at this logarithm here more carefully, because remember the logarithm, we can write it as the log of the absolute value plus I times the arguments. If we do that over here, we're going to get the integral But instead of just this logarithm over here, we're going to write the logarithm of the absolute value of the stuff inside, so 1 plus e to the t plus I times lambda, but then we're going to add this guy with I times the argument. Now, we have to be careful. What is the argument going to be approaching exactly? Well, we're coming from the top of these branch cuts over here. So let's take a look on our picture. What happens if we approach from the positive side? Well, take a look at the imaginary plots over here. The imaginary part of the function is going to be negative. So in particular, on our w plane, we're going to be approaching from down over here. Now, because we're approaching from underneath the branch cut in our output space, the argument's going to be exactly 2 pi. So we have I times 2 pi here, okay? And then we have a dt. And then we can do something very similar for the integral along the psi negative path. So integral along psi negative, a lambda, of the function f of z dz. That's just going to be equal to the same thing, but now we're going, instead of negative infinity to 0, we're going from 0 back to negative infinity. So 0 to negative infinity of, yeah. Now, because the imaginary parts, if you come from the other side, we're going to have a positive imaginary part. But what's the argument there? It's just going to be an argument of exactly 0. So in particular, we don't even care about this imaginary part. It's going to be 0. So we're just going to be left with the logarithm of 1 plus e to the t plus I times lambda, like so. Now, we want to add these guys together because remember in the sum, let's take the sum over here of those two paths. So what happens if you add the two together? So integral psi positive lambda plus integral psi negative lambda. Well, notice, first of all, this integral, you can reverse the bounds by putting a negative there. So now we have a 0 at the top here. And then we're going to start at negative infinity, just so it matches the bounds of the other integral. So we're essentially taking this integral, or the integrands of this guy, and we're subtracting out to this integrands over here. So if you do that, you're going to get the integral from negative infinity to 0 of exactly what? Well, this guy, if you multiply into this logarithm here, you're going to get t plus I lambda times the logarithm there, but then you're subtracting t plus I lambda times the same exact logarithm. So in particular, the logarithms are going to cancel, which is nice. So what remains is exactly this 2 times pi times I over here. So we have 2 times pi times I divided by, well, I forgot this factor here, so we have t plus I times lambda times the 2 pi I, then we divide by all this junk that's at the bottom here. So t plus I times lambda squared, and then squared dt. Okay, so that's what we end up with. And now, evaluating this integral, it's fairly simple to do. You can probably see it already because we have some quadratic down here, so t plus I lambda squared, and then we have this t plus I lambda up over here. So this just screams for the substitution integration method, whatever it's called. So let's factor out pi times I here, and then I'm going to leave the 2 times t I lambda on the inside there. So this is going to be some sort of integral. Yeah, we're just going to be left with 1 divided by. If you can try the substitution yourself, you could just let, for instance, u be equal to 1 plus t plus I times lambda, but then squared. If you do that, you're going to reduce it down to the integral of 1 over, let's say, u squared here, I believe. That should be right. So du. So what is this going to be? It's going to be pi times I. Integrating that is going to give you negative 1 over u. So we have a negative here, 1 divided by u, which was 1 plus t plus I lambda, but this thing is squared here. And then now we have to evaluate this guy from, negative infinity to 0. Okay, which isn't too bad to do. So if you plug 0 into this guy, you're going to get negative pi times I. Well, what happens if you plug 0? That's going to be a 1 and then plus I times a lambda squared. But I lambda squared, that's just going to be negative lambda squared. So that's going to be, I'm losing brain cells already, oh my god. So that's going to be 1 over 1 minus lambda squared. Okay, and then what happens if you plug in negative infinity into this t here? Well, you're just going to get infinity in the denominator, so you're going to get 0. So this is basically the whole thing here. right? And what we can do next is we can take this negative here, put it into the denominator, and what we get is something that looks like, pi times I divided by lambda squared minus 1. So this is the result of taking the sum of those two integrals above and below the branch cuts if we're at some imaginary parts of lambda, which is pretty cool. All right, so now what we have to do is we have to take the sum of all these guys. Now remember those lambdas there, those were just placeholders for 2k plus 1 times pi, just so we don't have to write that all the time. So now what we can try to do is we can try to evaluate the sum. So next step over here, we take the sum from k equals 0 to infinity, we have the pi times I divided by, now that lambda squared, that's going to turn into 2k plus 1 times pi, but this thing over here is going to be squared, and then we have a negative 1. All right, so what exactly is the sum going to be? You may have seen this sort of sum before, maybe not. I didn't know that this sum was a thing until I researched this problem. But what we can do is you can use a particular series expansion for the tangent. Let's just bring that pi times I out to the front here. And there's a particular series expansion for the tangent function which goes something like this. So we have tangent of z is equal to the sum running from k equals 0 to infinity. We have big fraction, and then we have something like 2k plus 1 times pi, and this thing here is squared, plus 2z is squared, I believe, and then we have 8z at the top over here. So this is one of the series expansions for tan that you can use, and this looks basically the same as what we have over here for a particular value of z. Let me just check if I got this series right, otherwise, yeah, that should be correct. Okay, so how do we evaluate the sum? We just need to figure out what value of z it should be. So first of all, we have 2z squared, which we want to be, that should be a negative there, I believe. Yeah, this is a negative. So we want this guy to be a 1. How do you do that? You just set z to be exactly 1. So this is equal to pi times I. We have the sum, k equals 0 to infinity. Let's do the denominator first, so we have the same thing here, so 2k plus 1 times pi, and this is squared. Now we're going to subtract. 1 is equal to 2 times a half, but squared. So this is z equals a half here pretty much. So z is equal to 1/2. So now we want to somehow get a 1 up over here. So we, of course, need to have 8 times 1/2 here, but 8 times 1/2 is 4, it's not equal to 1. So to compensate for that, we are just going to divide by 4 on the very outside there. So that should be it. That's what I had in my notes as well. Awesome. So what is this going to be? It's going to be pi times I divided by 4 times the tangent at exactly, 1/2, like so. So this guy over here, that is going to be the sum of all these integrals over here, this infinite sum, which is pretty cool. And now we're basically in the home stretch over here because we have the left-hand side figured out, it's this weird thing over here. And then we also have the right-hand side figured out, the value of this infinite sum and this I over here, and those two other integrals. If you guys want to, I might make another video evaluating those. I can't be stuffed today to do it, honestly. So yeah, let's just wrap up the video. Where should I do it? Let's get rid of all this branch cut stuff because we don't really need it anymore. So, in the end, what do we get? We're going to get pi over 2 and then 1 over 1 plus e to the negative I. This guy is going to be equal to, we have the sum over here, which evaluated to, what was it, pi times I on 4 times the tangent, okay? So we have pi times I divided by 4 times the tangent of exactly 1/2. And then we have plus this integral I, which was our original integral. Okay, so let's try to simplify this a little bit, I guess. So we have I is equal to, we have this guy minus this tangent stuff over here. So let's factor out. What exactly do I want to factor out over here? Let's factor out a pi over 4. Why not? So we have pi over 4. So we're left with this guy. So that leaves us with, that's going to be 2 divided by 1 plus e to the negative I. And then we subtract off I times the tangent of 1/2. Now tangent, remember that's sine over cosine. We can rewrite it in terms of complex exponential because we have a complex exponential here. Might as well try to simplify using complex exponentials. So we have e to the, that's going to be I times 1/2 minus e to the negative I times 1/2. And this stuff is divided by 2i, so that's the sign in the numerator. Then divided by the cosine, which is pretty similar. It's e to the I 1/2 plus instead e to the negative I times 1/2, but we only divide by 2 instead. So in the parentheses there, okay. So what can we do now? First of all, those 2's are gonna cancel each other out, so cancel, cancel. And then we have this I divided by I, so those are gonna be gone as well. So where can we go from here? Well, let's see. Let's try to make this denominator here looking like this denominator. So we have 1 plus e to the negative I. What we can do is we can multiply the numerator and the denominator by e to the negative I times 1/2. Okay, so let's try to do that. So this is going to be pi on 4. We have 2 divided by 1 plus e to the negative I. And then what happens if you multiply this guy by, well, what did we say? It was e to the negative I times 1/2, so times e to the negative I 1/2. That's going to give us minus 1, and then a negative e to the negative I, like so, I believe. And then what happens if you do it to the denominator? That's going to be exactly 1. And then we have a plus e to the negative I, like so. Okay, so now we can add the two fractions together. So this is pi on 4, and then times 2 minus 1, which is 1, double negative, so that's going to be plus e to the negative I, divided by 1 plus e to the negative I. Numerator, denominator, those are the exact same, so cancel, cancel. And the final answer is pi on 4. Oh my gosh, that was one ridiculous integral over there. But yeah, the value is pi on 4, which is quite a simple result. I don't even know how long I've been filming for. Honestly, this is probably like over 30 minutes, maybe 40 minutes. But yeah, I guess the only thing I left out was the integral over the gamma over here. I mean, it's quite easy to do if you just plug in the parameterization and yeah, find a nice bound from there. I might make a video, as I said before, on that if you guys want me to. But yeah, that's going to be all for this video. Hopefully you guys enjoyed. There's going to be more contour integration stuff coming up. I have a few contour integrals plans that I still need to write solutions for. And yeah, I'm going to be posting a bunch hopefully this semester as well, because I'm taking a complex analysis class finally, and also an algebra class. So if I see interesting stuff from any of those classes, I'll just put it onto the channel. But yeah, that's going to be all for this video. Hopefully you guys enjoyed. And yeah, up until the next one, have yourselves a wonderful day, and I'll see everyone in the next video. Bye bye.